Yes. Good morning once again. And I hope that you can hear me. Please let me know if you can hear me. You can text.
You won't.
We are getting you, sir.
Wonderful. Now, we've been looking at digital logic circuits, and really this is where everything gets interesting. And so we'll continue that discussion. We looked at gates. We looked at the idea of truth tables, but yeah, we looked at the OR operation, and we said that with the OR operation, it is either or. Tugume Mark, why is your hand raised?
Sorry, it's a mistake.
Okay, so we looked at the OR operation and we said that it is either or, meaning that for any of the inputs, as long as at least one of the inputs is a 1, the output will be 1, irrespective of the other inputs. And we said that the OR gate can have more than one input. It can have the OR gate has a minimum of 2 inputs, but it can have 3 or 4, 5 or 6. However, I mentioned that usually for those large input OR gates, we tend to combine a number of OR gates, and we are going to be looking at these logic circuits so that instead of using a 4-input OR gate, you can use 3 2-input OR gates. We looked at the example of the comparator. And so you have 2 scenarios where you have a signal coming from the temperature transducer and a signal coming from the pressure transducer. And the idea of the OR gate here is that either of these 2 can trigger the alarm. Okay, as long as one of them is out of range, it will trigger the alarm. Also, it goes without saying, obviously, that if both of them are out of range, meaning both are 1, 1, still you're going to have a 1 here that triggers the alarm. And then we looked at some examples, and we also went to I think we went to the AND gate. If I'm not mistaken, I taught the AND gate, did I? Where we said that here, both of them must be true for the output to be true. And what I mean by true is it is a 1. So
You were just starting to introduce Anne, and that's the time, I think, that our time.
Okay. All right. So let me then talk about the AND operation with AND gates. So just like in the OR case, we were saying it is either or. In this case, the 2 situations must be true. When I say true, I mean that it is a 1. When it is, when I say a 0, essentially I'm meaning, Nimusima Fiona, please keep yourself muted. What I mean is that if I say true, I mean a 1. If I say false, I mean a 0. If I say high, I mean a 1. If I say low, I mean a 0. And of course, I can say 1 and a 0 as well. Anyway, so you have 2 situations that must both happen for the output to be high. So imagine that in the case of our comparator here, of our system here, we could have a situation where we want both temperature and pressure to be high or true for the alarm to go off. So alarm to go off. So in other words, this AND is what we are calling the AND operation. Nemsima Fiona, I keep muting you and you keep unmuting yourself. I don't know why. So you've seen scenarios like those where, imagine also that you have a security system and you have a proximity sensor here and a proximity sensor here. And you say that for and of course you have an alarm or some notification or whatever. And you're saying that for the alarm to go off, this sensor and that sensor must both detect intrusion. Proximity sensors, basically, if you come close to it, it says true, meaning something is around. Now, the problem with that, this wouldn't work well because obviously an intruder cannot set off one alarm on one side and another on the other side. Sorry, the proximity sensor. So this wouldn't work it right in this scenario, but essentially that's what it like this. And we have two inputs, A and B, then we say that our output X is AB. You can say our output X is equal to A. This is the right scenario of how we write it. But because we know that's like multiplication really, and because we are using this a lot, we end up saying you'd end up using just AB. But what AB means is that it is A and B. Okay, it is not A times B because this is not ordinary algebra. Nemsima Fiona. I don't know if she can hear me, but you keep unmuting yourself. Or maybe your thing has a problem, but then you're giving us feedback. A and B, where that is the AND operator. And you can see here in the truth table that we have scenarios 0, 0, 0, 1, 1, 0, and 1, 1. All the inputs must be high. In other words, for our output to be true, all the inputs must be true. And you can see that in this case, we have only one scenario where the two inputs are true, giving us a true output. If we extended this to more than two inputs, we would have, let's say, A, B, C, and our output X would have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And based on the description that I've just given, this is the only situation where you get a high output. The rest is 0, 0, 0. So in other words, your inputs, whatever number they are, need to be high for the output to be high. That is how AND operation operates. If we look at this, we have two inputs, A and B, and we have an AND gate. So if you're looking at this, we say these are timing diagrams. You're looking at for points where both inputs are high, because those are the points where you're going to get a high. And you can see that generally here both are low. Here this is low. So the fact that there is a low input will make the output low. It is in this situation where both are high, giving us a high. But from this point, A goes back 0, so everything goes back to 0 until this point where you have a high here and a high here, giving you a high again. So you can see that when you're dealing with timing diagrams, you're looking for those transitions for each to see where your output, let's say something like this. Something like that. So you're looking for transitions. So here I can see that's a 0 and a 1. Let me say these are my two inputs. This is a 0 and a 0. So my output X will be a 0. At this point, that goes high, but B is still 0. So I will continue. But this point, B goes high and finds that A is high, but A comes back low at that point. So I'll have a 1 here. But because A has gone to 0, I will have a 0 again. And because A is 0 all the way, I'm going to have a 0 as long as A is 0. But between this point and that point, A goes to high, but B goes low again there. So I'm going to have a high here. Okay, because B is a 0, I will remain low until B goes high. But when B goes high, A is 0 anyway, so I will continue. at 0, something like that. Okay, now if we look at this is 0, that is 0. So we know that our x will be 0 up to that point, and also 0 definitely up to that point. And then we look at what is now, because now b is 1, the a, whatever is at a now will determine what is at 0. So you can see a goes high at that point. So we are going to have that. It goes low at that point, goes high at that point, goes low at that point, and so on and so forth. So we are going to have a like that. Okay, now if you notice, it's like between this point and that point, a has gone to the output, right? Because as long as b is 1, a is just going through, meaning that when a is 1, the output is 1. When a is 0, the output is 0. When we use gates like this, we call these, you can see the idea of a gate actually coming out here. This is an AND gate. It means that depending on what b is, a can go through to the output. And so that this circuit now acts like, this circuit now acts like a gate. It's like you open the gate and something goes through. We call b, in this case, or a scenario like this one, we say that b, input b, is a control input. And what it means is that you can see that it controls whether a goes through to the output or not. So when it is 0, a does not go through. When it is 1, a goes through to the output. So that is really the idea of a gate. And when we use this like that, we call b a control input, because clearly it is controlling when a goes through or not. So for instance, this could work. Let me just find a scenario. It could be any scenario. Imagine that, I'm trying to find something that is clear in real life, but it could be like light. Imagine that I have my AND gate here, and I have a light signal. That light is, it could be a flashlight, and I have my B. This light might be 1. 1 might mean light on. Okay, so I make sure that here I have a 1, meaning light is on, but using B, I can determine whether light actually goes through to the output or not by making B either a 0 or a 1. If it's a 1, light on. If it's a 0, light off. So the light here will be on, but I just don't allow it to go through to the output, where that output might be the whatever that is. You could think of different scenarios here, but that's essentially how that is going to work. And you can see this is the correct output we have just found out. Now we have our remember we said that we have 3 basic operations. We had OR, we had AND, and now we have NOT. So NOT the gate is this one. By the way, let me emphasize that the OR gate, remember, was drawn like that. Okay, with your inputs here. Now the AND gate is similar, but for it, this is flat. It is straight. Then you have that. So you have to draw a gate that I can understand. I'm not saying be not, but your OR gate shouldn't look like your AND gate. Now the NOR gate is written like this. Okay, you draw a triangle facing in that direction, and you put a dot there. This is X, and you have your input. Now the see my made our life difficult. I don't know why. Now NOR gate, the difference between the NOR gate and the other gates? Oh. The difference between the OR gate, the AND gate, and the NOT gate is that the NOT gate has one input. The others have 2, 3, whatever number, but the NOT gate always has one input. And what it means is that X is equal to A with a bar. That means X is not A. That means X is not. So what is here, what you get at the output is the opposite. If A is 1, not A is 0. Because remember here we have conditions. If A is 1, not A is 0. And if A is 0, not A is 1. As simple as that. And this bubble is put there to show you that it is flipping the sign. So the bubble shows inverse. Now this gate, this operation, the operation is also called an inversion or complementation operation. So we can say inverse operation or complementary operation. I can also say that actually, so sometimes in fact, not gate, we call it an inverter, because you can see in its truth table that if A is 0, the output is a 1, and if A is 1, output is 0. So what it does is really reverse the input, and that's what we call it, an inverter. Yeah, simple as that. As you can see here, if you have your input like that, the output is simply the opposite. My signal is that the output will be 1 here, and a 0 here, and a 1 here, and a 0 here, and a 1. It is as simple as that. It is a very simple operation that we can you can call it an inverter. And we know that it inverts because it has that bubble, this little bubble on the gate. You can see this is the first time we've met a bubble like this on the other two gates, because this is an inverter. Later on, you will realize that you can also draw your NOT gate this. Okay. Even is allowed, but I would recommend that at this stage we continue this one. By the way, we are about to find other gates that have bubbles, OR gate and a gate that includes some bubbles. But until for now, that is that is the future. Job, I don't know what you mean by modern and AC inverters. If you mean these ones you use in things like solar, no, they are different things. This is digital, so we are looking at really basic operation. Now let us look at an application. Where might you use NOT operation? Imagine you have your 5V, okay, that is a voltage, and you have some, and you have ground. This is some resistor. All right. So if you look at this, we have a push button. This push button, if you push, it means that you have connect complete circuit. If you don't push, then the circuit is open. What happens when the circuit is open? If the circuit is open, you have, obviously, we know that the potential of 5 voltage is 1, it is a high, and the potential ground, GND in digital, is a 0. So if this is not pressed, then you have a 0 here, meaning that you have a 0 there, because this is open. And if you have a 0 here, you're going to have a 1 there. And so if I see a 1 at this point, I know that the button is not pressed. all right? Now, if you push this button, it means you have completed that circuit. If you complete that circuit, this 5V is at this point. Obviously, it's just a line. So that 5V is at this point, meaning that we have binary 1 at this point. That's still binary 0, but this 5 voltage will appear here. And if this is 1, then the output here will be 0, and a 0 will tell me that I have pushed the button. So maybe at this point, at this output, you could put this in a LED, okay, or some type of lamp, okay, and your lamp will light when the button is not pressed, right? When it is not pressed, remember this 0, that is not connected. So you have a 0 here, okay, from ground, and you have a 1 here, and this one going into your lamp will mean it will light. If you press, this 5 is here, which is 1. 1 changes to 0, meaning that you have a 0 going into your lamp, which will not, which will go off, because a 0 going into a lamp is not going to light it up. So that is the NOT operation, and you can see this is a very simple application scenario that can help you to determine whether your button, like a push button, is pressed or is not pressed. I would ask you to give me some examples of push buttons. But for instance, when you go home and you have a push button at the gate, right? Those alarm things that you use to notify people in the house that there is somebody at the gate. When you press it, now that one, the operation would be different from this one, right? Because you want that when you press it, you have a 1 here, and that one will go into the bell to ring the bell, and you would want a 0 so that if no one is pressing the button, you would want a 0. Yes, Emmanuel?
Yeah, I think in the real life scenario is the DSTV remote. When you complete the circuit by pressing any button, the light, the power light comes on the remote.
Yes. That is also, yes, that's true, Emmanuel. That is also, by the way, a push button. So, if you've ever seen the board of a remote inside there, if you are lucky enough to have broken it and looked inside, they are like push buttons, really. So they act all in the very same way. Generator, push button, and so on. So in fact, push buttons are very common, and there are many examples. Thank you. Now let us look at a summary. So we have NOT. If we have NOT 0, it is a 1. If we have NOT 1, it is a 0, because the bar means NOT. Okay, so if I say NOT 0, I am trying to invert 0, which will give me a 1. Now for the AND, 0 or 0 and 0 will be a 0 clearly. 0 and 1 is a 0, 1 and 0 is a 0, 1 and 1 is a 1. So only when all the inputs are 1s do we get a 1 when we are dealing with the AND gate. In the OR scenario, 0 or, that's not plus, 0 or 0 is a 0. But all these others, there is at least 1, 1, at least a 1. As long as there is a 1, you're always going to have a 1. So this is just to recap. That is the summary of operations. So now that we understand the operations, we can begin to build some simple circuits, right? After that, we will be able to build some really complicated circuits. You can build a circuit of any level of complication, but let us look at some simple circuits. So in this case, we have 2 gates. Okay, so when we build circuits, we combine different gates, and so these different gates can work together to perform some different functionalities. In this case, we have two inputs, A and B, and we have an AND gate. And here we have clearly an OR gate. Now the output of the AND gate becomes an input into the OR gate where the other input is a C. So the best way to start looking at this is to start from this side and keep building your circuit as you go towards the output X. So I can see A, B through the AND gate. I can determine that this is going to be A and B. And now A and B is ORed with C. When I say ORed, I mean OR. Okay, what I mean is that they are put through the OR gate. Okay, so the word ORed or ANDed, you know, we sometimes use it a lot. So for instance, here I can say that C is ANDed with whatever that is. Now, anyway, we have A dot B, okay, which is A and B, and then we have C, meaning that our X is going to be A and B, okay, as one entity, or C. You get it? So this you can write this as AB or C. Now, what does this mean? This means that the output, it means that the output, remember this is an OR gate because we have an OR. So we can say here that output X is high. You see here, you have to learn English, eh? But you guys went to good schools, so you know English. X is high when either AB is high, or where that is the OR gate, or C is high. Obviously, it goes without saying that even when both are high, that's okay. Now, when is AB high? When can AB be high? Can anyone type in the... When can AB be high? Yeah. Yes, when A, so AB is high when A is equal to B is equal to 1. All right. So can you give me the output here, X? What will X be here? Oh, guys, if you notice in the chat that somebody has already written the right answer or has written your answer, you don't have to keep putting, because the point is not to get many correct answers, just one is enough. So for this second diagram, can you help me? How do we express X in terms? So when we create circuits, we want to describe the output in terms of inputs. And we said that that is similar to ordinary algebra, where we can say Y is equal to MX plus C. This is your output Y, and your input is X, essentially. A, B, and C. Great, thank you guys. So here we have, this is the OR operation. So the output is A or B, and then you AND that with C. And so your X becomes A or B and C. Now the problem here is that you have got to use brackets. If you do not use brackets, then we don't know whether B and C, this can become something like A or B and C, okay? Or it can be A or B and C. So we have got to be very careful when we are using the OR, because we have to use brackets to all things together, and then we can AND them later. Otherwise, you would be in trouble. Obviously, a scenario like A or B or C, this one wouldn't matter, because whether it's A or B or C, or whether it's A or B or C, this one is okay. And you know, the theorems of algebra, those commutative properties and whatever, they hold even in Boolean algebra. But in a scenario like this one, we have got to use brackets to show clearly which one is ORed with which one. And then after that, we can AND them with C. Great, great stuff. Sylvia Nabukera, you are creating feedback. Okay, so this is yes or report. This is the correct answer, and you can see we got them right. You can ask.
Morning, doctor.
Morning.
Kindly, I have not got on the first scenario well, because for the first circuit it says and, then the second is or, and we say for and operation it has to be 1 1.
Yeah.
Then the or operation, either of the two can apply.
Yeah.
So now I'm not getting it clearly. In case, for instance, on the and, as I said, n of either A or B is true. That means that the and operation will not be on, will not be high.
But you see, if C is high, then it doesn't matter whether A and B are low. X will still be high. You get it?
Okay. Okay, good.
So that's why we said in my description here is that X is high when either AB is high, but if AB is not high, then or high, then C should be high. So as long as if A, so imagine, let's say if A is 1, B is 0, to be 0, because 1 and 0 is 0. But in here, this is the O. So if we say 0, O, as long as this is 1, we are still scenarios where I can give you. Yes, please carry on.
So doctor, does that mean that in case now we have like 2 bits, then it can, the situation can happen?
What do you mean when you say 2 bits? I don't get it.
Okay, for instance, now if we say A has 1, then B has 0, then we say also either C has 1. So the one
and C is 1.
Yes. Then we shall have 1, 0, 1.
Yeah, something like that. But let me put this in your equation. So X we have seen is A and B, and we will need. That means we have 1 and 0 or 1, right? And what is 1 and 0? It is 0 or 1. And what is 0 or 1? It is 1. Okay. And if we were to use it here, we would find that X is equal to A, which is 1, or B, which is 0, okay, and C, which is a 1, which is 1 or 0 is 1, and 1, which is 1. But now imagine A was 1, B was 1, and C was 0. If C is 0 already, we know that whatever that is, as long as C is 0, this AND gate will give us a 0. It doesn't matter, you know, as long as C is a 0. But even if you use your equation, you can see that X is equal to be 1 or 1 and 0. At this point, I don't need to go further. But even if you wanted to, you can say 1 or 1, which is 1, and 0 is clearly going to be a 0. Okay? I don't know if you get it.
Yeah, I get it now.
Okay.
Hello, sir.
Yes.
I have a question whereby just of recent you've talked about a control input. Is it that in this arrangement of NAND and O, rather and O, is it where we are having the control inputs, and which arrangement should we take as the control input? Is the arrangement of A and B or the C stuff?
The O one. No, it can be either, by the way, and we are going to, it's just that I've brought it up, but it's more in the next chapter when we look at inhibition gates and control gates. But generally with control gates, it's better to use the AND. Okay, because the idea is that you want to pass the one of the inputs to the output or not. And the AND does it very well. Because you can see for it, as long as B is a 0, A will never go to the output because it will always be a 0. But we can also use other types of gates, as we are going to see later on. For now, you can take it as an AND gate, but I've really just brought it way ahead of its time. So Asimo is asking, please, I think for AND gate, it should be indicated whether both inputs are high. Otherwise, I see in our previous example being C, if A and B are 0. Yeah, and no, of course you use what you're given, okay? And you can see in the truth table, we are going to be dealing with all the possible scenarios anyway. But essentially, if you look here, as if, so for instance, we have X, let us look at this case. X is equal to A or B and C. In a scenario like this, and Pascal has just been asking about this one, the C input is a control input. Why? Because if C is 0, it doesn't matter what A and B are. They will never get it because X will always be 0. But if C is 1, then we have whatever we have at A and B going to the output. So X will now become A or B and 1. Anything and 1 is that thing. That means A or B. So meaning that if A or B is a 0, 0 and 1 is 0. If A or B is a 1, 1 and 1 is a 1. So you can see that whatever A or B is will go to the output, making C a control gate. But we are going to describe this further on in future. For now, we can leave it at that. So, operator precedence. This is something that we have already talked about. If there are no parentheses, because sometimes we don't use parentheses, parentheses are those brackets. If I see something like A and B or C, you know, this could be either A and B or C, or it could be A and B or C. In all cases, and takes precedence. If you find no brackets, you should do the AND operation first, meaning that this part will be correct and this one would be wrong. If you are given this one, you should first deal with the AND operation, and then whatever you get, you can OR it with C. But usually it's better to use brackets so that it's very clear. But in case it's something confusing you, you should always do the AND operation first. I hope that is very clear. It's really easy. And I had put here to look at the previous slide again, but in fact, we know what it is. Let's say we have something like A, B, C, or which is A and B and C or D. So what do you do here? Clearly, if AND is taking precedence, you're going to first deal with this term, and whatever term comes out, you OR it with D. Otherwise, somebody could do something like A and B and C or D, and the outputs would be totally different, but this would clearly be wrong. But of course, we can have this one if that's what the scenario is telling us that we are going to have. As long as you develop your circuits, you make it a habit of using these brackets. So this is like BODMAS. If you know, I remember we used to have BODMAS. I don't know if you people still use it, but you're looking like at the precedence of these operations, and you are looking at which one should go first. And I'm saying that in this case, the AND operation, the OR operation. Now let us look at inverters. We have an inverter here. We have A, it goes through an inverter, and then it is ORed in here. And then we have B, which also goes through, B does not go through an inverter, it goes straight into A. So here in front of the inverter, we have A inverse, so that if A was a 1, the A inverse is a 0. If A was a 0, the A inverse is a 1. And then at the output here, we are getting this input, which is A inverse. We are ORing it with the B, meaning that my X is equal to A inverse or B. All right. Can you do this one for me and tell me the output? When you write it in the chat, you can, instead of the bar, you can just write bar and you put whatever in the bracket that you are barring. Yeah, or not. Yeah, this is actually really nice. I hadn't thought of that, which is not. And so really what this is A or B inverse, the whole thing, not just individually, because A inverse or B inverse is not necessarily equal to A or B inverse, okay? It is not necessarily the same. Right, thank you guys. So what does this mean really? It means that if our A, let's take an example of A is 1 and B is 0. So our X is going to be A is 1 inverse or B is a 0. And so 1 inverse is a 0 or a 0, which gives you a 0. In this case, our X would be A or B, and A or B is 1 or 0 inverse, which is 1 or 0 is 1, so which is 1 inverse, which is also a 0. Now let us look at what if we had ended up with this one. We would have 1 inverse. 1 inverse is 0, and 0 inverse is a 1, which is a 1. And you can see clearly that a 1 is not equal to a 0. So when we have an inverse over a number of terms, make sure that you write your inverse over all terms. If you write it over terms individually, then you're going to be in trouble. Just one moment. Okay, so that's good. Usually when I teach physically in class, and I'm not going to teach physically for a long time because of COVID, but when I teach physically in class, I make you do these things. So it's important that even as I write, even you have some paper where you're writing. Don't attend like this is a history lecture. Please write, and I thank those guys who are doing that and giving me answers, because with the digital electronics, that is the best way to learn. You need to be writing down. You can't just be reading like you're reading essays. So I'm going to give, I want you to do this one, but I'm going to do this one with you. And I said, you see now this is a rather complicated. Abigaba Colin, I don't know what you mean by physicals are beginning in November, but mine are not. So you can see that this is a rather complicated circuit, but it is really not once you have learned this stuff. So let us do it together. We start from this side. We can start with this first gate. So we have a gate A, B, C, D, E. We have 5 inputs, and you can see the inputs go into different. This is an OR gate, so it is A or B, meaning here we have A or B. And this term is ANDed with C because that's an AND term. And is inverted, meaning that here you have A or B and C, and the whole term is inverted. So your inverter must go across the entire term. Now this term is ORed with D, meaning that at this or B, and C, and this is inverted, or D. Okay, so your inverter must stop then, meaning that that term is now ended with E, meaning that now my X, I can say my X is equal to A or B, and C, I or D, okay, and then I can put the whole thing in bracket, and I end with E. So that is my term. Looks beautiful, doesn't it? It is quite large, but it is nothing scary. And the beauty here is that very soon, if I give you that term, you can actually draw for me that circuit. Now let us look at a scenario. Like, let's use some terms. Let's say maybe imagine that A is equal to 1, B is 0, C is 1, C is 0, D is 1, E is 1. You see, in this moment, if I had said that E is a 0, I don't even need to bother with what's happening here. My output will be a 0 because I'm ANDing E with the whole thing. But let's take the scenario of E is 1. So let's look at this. X then becomes 1, or B, which is a 1, okay? Oh, B is a 0. So 1 or 0, and C is a 0, and I invert that. Or D, let me say D is a 0. Or D, which is a 0, and the whole term ended by 1. So 1 and a 0, sorry, 1 or 0 is 1. So that is going to be 1 and 0, and this is inverted, or 0 and 1. And then 1 and 0 is 0, so it's 0 inverted, or 0 and 1. 0 inverted is a 1, or 0 and 1. 1 or 0 is 1, so you end up with 1 and 1, giving you a 1. Any questions on this? Oh, these guys have already done it. Brilliant. Okay, great. So yours is this one. You tell me the you tell me the output circuit. I'll just give you 1 minute since it seems you are doing it very fast. You give me an equation for X. Okay, so I'm seeing here, let me start with Daphne. Please stop there. If you are typing, please stop. I want to use, let me pick one of these. Let me pick Daphne, who says that X, she says that X is equal to A and B and C. and then A and D. Okay, so she says that I don't know why my pen is not working all of a sudden, but okay, so Daphne says that X is A inverse and B and C, A or D inverse. Let's see. So this is A inverse, and this is an AND gate. So you have A inverse or B, sorry, A inverse and B and C. Here you have A and D, or A or B, A or D, okay, because this is an OR gate. And here you have A or B, the whole thing inverse, and then you have an AND gate, and she's correct. So yeah, so your output is X is equal to A inverse and B and C and A or D inverse. Now, what if X is, sorry, what if A is equal to B, is equal to C, is equal to 1, and D is 0? What is X? Now, Mark Collier, if you say A inverse B, C, and okay, I've seen that that's a 0, so that's okay, you can stop there. You have A, I think Mark has A inverse or D inverse. This is a very big problem because this term, you can see that the whole thing is inversed here. So if you write it like this, you're going to be very wrong, okay? You have got to write it like that. Okay, so we've gathered that the answer is 0, so we'll take it like that. Because I think actually the reason is that you have a 1 or a 0 here, and which means, and you have an inverse. So 1 or 0 is 1, inverse is 0. And when you put a 0 here, it makes everything a 0. It wouldn't matter what it is. And you can see that obviously you got them correctly. These are very complicated diagrams, but you have got it very easily, which is wonderful. And that's the beauty with digital electronics, that no matter how big something is, there are very simple principles that you can use to get it correct. Now, the people who can't get to this, for them, the issue is that they can't get anything. So in my class, people will score 80 and 90%, and then a lot of the people will score 30 and 20%. I've never understood it, but unfortunately, that's the way it is. It's like you either know or you don't. By the way, I've not forgotten about our quiz. I've not forgotten about our quiz. I am going to give the quiz, okay? So don't leave. Wonderful stuff. Okay, so that is actually what we were doing. Right. So let us look at this. We can evaluate our circuits using what we call truth tables. Okay, we can evaluate our circuits using truth tables. What we need is to put our 8 terms. In this case, we have 3 inputs. So 2 to the power 3 is 8. That means there are 8 different combinations, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1. And then we go and look at the intermediate states. The intermediate terms, we need an A inverse. So you can see we have got an A inverse. On this side, we need A inverse B. So we have A inverse B here. And then here we need BC, which is a term that comes from these 2 through here. And we have BC here. And then BC and AB go through an OR gate to get us X. So we have X is V plus W, which is really X is A inverse B plus BC. People have a next lecture. What does Isaac mean? Hopefully my network is better. I don't know about your network, but my network is hopefully better. So anyway, so we need to first get the term A inverse. And the A inverse here, we are looking at A, so the inverse is just the opposite, 1, 1, 1, 1, 0, 0, 0, 0. And then we get A inverse and B, meaning that we are multiplying this and these terms. So like 0 and 1 is a 0, 0 and 1 is a 0, 1 and 1 is a 1, 1 and 1 is a 1. And because all these are zeros, it doesn't matter what B is, these are all going to be zeros because we are ANDing. Then we AND B and C. It is B and C, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, we finally have a 1. B and C, this is 0, 0, 0, 0, 1, 0, because we are ANDing, 1, 0, 0, 1, 1, another 1. And then finally, we can use our OR gate here to all these two terms, these two columns. So you have here 0 and a 0, because this is 1 and 0, 1 or 0 is a 1, 1 or 1 is a 1, 0, 0, 0, 1. Okay, as simple as that. So we can feed our truth table using, by the way, let me ask a question. Why should quiz should be in the next digital electronics lecture? Why is that? Or query? I mean, I don't get it. But I'm going to give the quiz today, whether there are 2 people or 1 person. So let us also look at how we can implement circuits using Boolean algebra. You can try and practice with this. So for instance, you can find that in your truth table, you have that, you have that, you have that, you have that, and then you can do that. It's quite easy. Let us look at how we can implement circuits using. I can give you this expression and I tell you that you should do for me the circuit. So what you need to do is, first of all, to identify what is happening here. Here you have an AND. So that means we are going to have an AND gate. And an AND gate, its 2 inputs are going to be the OB and that term, which is B inverse or C. And then obviously here you have your X being A or B and B inverse or C. Now, what do we need here? Here we need an OR gate, and here we need an OR gate as well. But even before we reach that, we need a NOT gate here. So that means that for this, we already have our AND gate at the output, okay, which is X. Here we are going to need an OR gate, okay. And this OR gate has A and B, right? And then on this side, we are going to need another OR gate, okay. And the first term is actually C. Okay, so we have C here, but this term, I could just write B again here, but then we already have B here. But the B going in here is inverted, so I can put an inverter here, and I do that. So meaning that B goes through here, and by this point it is inverted, and you have C here, meaning you have B or C. Here it's A, B, you have A or B, and you'll get your output, okay? It is as simple as that, and as you can see, this is the diagram. You have A ORed with B, and down here you have B, you have to invert B, and you OR it with C to get the second term, and you can AND them because that is clearly an AND. Now, Sasra Ivan, I'm not going to upload it on Muere, because if I upload it on Muere, in my opinion, it's no longer a quiz. What is the problem? You people wanted online studying, and yeah, we have challenges, but anyway, so I think maybe you guys think that this is open to dialogue. So this is now 11:30. I'm going to give you 10 minutes. Actually, 10 minutes is a lot. Let me see. I'm going to give you 5 minutes to do these 3 numbers in the polls. And I'm going to launch the poll in the next 1 minute. If you have network issues, that's sad, but I am not in charge of your networks. So these are 5 minutes, and those 5 minutes are going to start in 1 moment. Please get your pen and paper and do this quiz. And this is quiz 1. We are going to be doing a number of quizzes. I think if you've asked some old students, because I know you are in first year, if you ask people in second year, third year, they'll tell you that quizzes are part of how I teach, and they actually really help students. So like today I have 154 students. I've been having 98. So students come to school, they learn, they pass. That's what we want. So in a way, I'm not a bad guy. In a way, I'm a good guy, but obviously it doesn't matter whether I'm nice or not. Okay, so I've launched the quiz. I'm sure that you can see there are 3 numbers. You have 5 minutes starting now. Remember that I usually end the poll, so it doesn't matter. For me, after 5 minutes, I'll end the poll, and that will be that.
Manchester United have got a former striker. Manchester City have got an elite manager. Chelsea have got an elite manager. Manchester United have got a former striker.
We have 2 minutes, please. Okay, please make your final, please make your final choices because I am going to end the poll. In fact, since I want to be nice, I'll add 1 minute. I'll end it at 37 past or 23 minutes to the top of the hour. I can see that people have not yet answered. Please make your final choices. I'll be ending the quiz shortly. Particularly on the last number, I still need many more people to answer. Have answered. Please, if you have kids around, you can. You see, guys, when you're preparing for class, it's important that you take it seriously. Assume that you have gone to campus so that you are not home. Otherwise, you are not going to pay attention to both. There are 12 people that have not yet answered. Unfortunately, our time is over. So I don't know what to do for you. Okay. So I'm going to share results with you. By the way, if you have not used your name, I'm not going to know who you are, because obviously this is going to record automatically in my system, in my account. So if you've not used your name, I won't know who you are, so I really won't even be able to give you marks. But for those of you who, you can see how different the answers are. Okay, this is why we do quizzes, because one was getting the same answer, then I would understand, but clearly here, there is an issue. If you add odd parity here in number 1, you already have 4 ones. If you add odd parity, you add a 1, okay, meaning that you're making them 5 ones. The question is, where do you add that 1? You add it at the left-hand side. So the parity bit is always the most significant bit. And so people who chose number 1 got it correct. You can see there are 14 people, 28 people, and 12 people who have got it wrong. Meeting a lot of information over a very long distance, what would you rather use? The people who said serial transmission have got it correct. Yes, it is a lot of data to do it slowly, but for long distance transmission, we always prefer to use this is hex counting. After 87FF, you basically have, because F and F are at the maximum, you have 8 in the, is that thousands position, and then 7 in the hundreds position. Those are not yet maximum. That means you're going to increase the hundreds F back to FF back to 0. It is, you're going to increase 7 to 8. Leave F where it is, the ones in the ones in the tens position, and then put F of the ones position you're going to have. So I think the people who, but I think here I need to think again. I think it is 8800. Yeah, so the right answer is 8800, meaning that you're going to increase 7 to 8 and then restart from 0, 0. Yes, that is the right answer. Thanks for participating. 148 of you participated. 3 people did not participate. I had 151 people. Now I'm seeing in class we have 156. Anyhow, we are all learning, and it is an experience. I'm sure with time we'll get it better. By the way, I should tell you that these quizzes in the end take like 5%. So it's not like you're going to fail because of quizzes, but I think it's important that we do them. We are going to do another quiz. Musa, we are going to do another quiz soon. I can see that you are happy, you enjoy them. So I want you to try implementing this circuit where you are. Unfortunately, you cannot show me, but you take 1 minute, implement it, and then I will implement it here, and we can compare. If it were in class, you would do it, and I pass around and see what you've done. Okay, so we have, by the way, what time is it? I don't know what, we are still in time. Okay, so we have an and here. And another and another and. We have 3 inputs, and then we have an or and an or there. So if we wanted, we could have a 3 input OR gate so that we have that and that and that through the same input OR gate. Okay. But we can also first have these 2 terms or, and then OR them again with that one. Okay, so let's see. Let us say that I have A, I have B and C, meaning that I have that one. So this gives me AC. Then B, I need another AND gate, and this is C, that is B. So the other input should go through an inverter to give me C inverse, okay, meaning that C inverse, and that is B, C inverse. And then my other AND gate should be, I can use a 3-input AND gate. Let me show you how I can do that. I can have B here, and then A, meaning that's A inverse, obviously that is C, meaning I have A inverse BC here, and I can pass this through an OR gate, meaning that I have AC or B inverse C, and then I can pass this back again through. Please don't do this, but let me do it since I've run out of space. I can put this through another OR gate, meaning that is my X. Now, what I could have done here, I think somebody's parent is asking him or how what they are doing. Paul, I will be with you shortly. What I could have done here is actually, I could have had A, B, and C, meaning that instead of having a 3-input AND gate, Fiona, today what you have done to us is incredible. I could have had, sorry, by the way, that is A inverse. I could have had my A inverse through an AND gate with B, meaning that I would have A inverse B, and then I pass that through another AND gate, you know, with C, so that I have, that's A, so that I can have my A inverse BC. So you can see that there are so many ways. Here I could have used the 3-input AND gate, or gate, sorry, but you can see I used two 2-input AND gates and so on and so forth. Agilit Bridget, it is not my, your poll is confusing where our marks, but I don't understand you guys. Now, the way you speak to your lecturers is you need to polish up, yeah? The way you talk to people. Leave the rest to me, okay? Don't care about your marks anyway, it's my business. For Mukalas Ivan, who is asking a more reasonable question, is there an advantage of using many gates? Actually, no. The idea is to use as few gates as possible, because you remember each gate you buy it consumes power and so on. So we want to use as few gates as possible, but you may, if sometimes you have access to 2-input gates rather than 3-input gates. And so that can be a bit of a problem. But generally, the fewer the number of gates, the better. Just to be specific. To answer your question directly, the fewer the gates, the better.
Excuse me, sir.
Yes, yes, Pascal.
At the end, I'm requesting to get me back the other screen where you have written.
Okay, is this one or this one?
Yes, yes. At the end where we are having the two all gates.
Yeah.
Can't we have only one OR gate, or it changes the arrangement? Because I can see why as an OR operation of AC BC complement, A complement BC.
Yeah, we could have one big gate, okay,
with 3 inputs.
With 3 inputs. Yes, we can do that. So I was saying that if we don't have a 3-input OR gate, we can use two 2-input OR gates to do the same operation. I think.
All right.
Yeah. Yeah, that's a good question. I think in general, in terms, so that I do not confuse you, because I think you can see this is actually the final term, which is what we have done. Only that here now we have a 3-input OR gate, which is what Pascal has just been asking about. Here we have a 3-input AND gate, okay? And so I think generally we want to use as few gates as possible. If you notice here, if I use this type of scenario, I'll have 1 gate, 2 gates, 3 gates, 4 gates, 5, 6, 7. In fact, if instead of this one, I use that one, I'll end up with 8 gates, which is a lot. And if you look here now, you have 1, 2, 3, 4, 5, 6. So instead of 7 or 8 gates, you can actually use 6 if you have these larger input gates. So yeah, maybe if I bring a question like this, I would be able to tell you whether we have whether you can use only strictly 2 input gates or you can use larger input gates. So yeah, that one I would have to specify. Otherwise, the circuits would do probably look different, which is something we want to avoid. And then a Cuthbert timing diagram not gate, especially when no input. I don't know what you have written, but please, you can rewrite that one so that it's more understandable. So yeah, this one is very easy. So we have X. How many gates would we have here? Already you can see there is that inverter, and then there is that O. So we know here we are going to use 2 gates, 3 gates. We have an inverter, we have another inverter. This is X, that is Y. And then we pass this through an OR gate. And we have our C. As simple as that. Yeah, well done. So let us look at another couple of gates. Now we said that we have basic gates, and those 3 basic gates are AND, OR, and NOT. Now we have another 2 gates called NAND and NOR. These gates are not basic gates. The reason they are not basic gates is because we use basic gates. We combine basic gates to form them. So that is why we don't refer to them as basic operations, because you actually create a circuit to create a new gate. These gates, we call them NOR and NAND. And we are going to create gates, once again, which are not basic gates, but that will bring our total number of gates that we are going to cover in this course to 7. Okay, so for now, the NOR gate, when you look at NOR, it is a NOR. So you have the OR operation, you take its inverter. That means that for OR, you have A or B. For NOR gate, you have A or B inverted. And so if you look at this diagram, we have added a bubble. So for the NOR gate, you draw it like that, like the OR gate, you just put a bubble there. Remember, we said that a bubble means an inversion. So there is no ambiguity here. Essentially what it is, and this is what I emphasized, is that you have an OR gate followed by a NOT gate. And so this combination is what we write as that. And you can go and buy an OR gate in a shop, but really what it is a combination of an OR gate and a NOT gate. And so it's almost like we just move this bubble there and we create our NOR gate. This is the expression. If you look at your truth table, you have 0, 0, 0, 1, 1, 0, 1, 1. For OR operation, it is 0, everything 1. For the NOR operation, now it is the inverse. So it is 1, everything else 0. If you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So for the OR operation, this would be a 1, the rest would be 0. Let's say OR. 1, 0, 0, 0, 0, 0, 0, 0. Now for NOR, it is the opposite. That's a 0, everything else is 1. So that is your NOR gate. And the other one is the, yes, Segawa. Segawa, you have a question? We cannot hear you if you have a question. So we'll just continue. Now, if you look at the NOR gate, by the way, this can be confusing. You need to probably do a small truth table every time you deal with these until you are very sure that you remember them. So the output should be 1, 1, 1, and 0. So you're looking for, is that Segawa? Segawa, can you ask your question? Now I can.
Oh, okay. My question is on this truth table you have just drawn, the one you have drawn.
Yeah, yeah.
So we're having an OR gate. I thought,
yeah,
in an OR gate, you get logic 1 if one of the inputs is 1.
Yes, you're right. Yeah, this is a mistake. Thanks for pointing that out. So yes, so we are going to have a 0. The rest is 1. Okay, sorry, I was very quick with that. And here we are going to get a 1 and the rest is 0. Yes, this is the correct table. Now, it's almost, a NOR gate is almost like an AND gate, but it's one, the AND would be down here. Joan? Thank you, Sego. Joan?
Good afternoon. Is it possible to have, yeah, good afternoon. Can you still hear me? Can you hear me?
I can hear you.
Is it possible to have an inverter, like to have them?
To have them?
Is it possible to have the A and B inverted and then again inverted after? Like NOR
Yes.
before and then again after.
So don't go off. Let me just draw something here to make sure that I understand what you're saying. So you're saying that because we are saying that we have this as our NOR gate, A, B. So are you saying that we what? We first individually invert A and B, then OR them.
Yes. Then
and then
again
we invert that again. Or
is
are you saying that?
Is it possible to do?
Are you saying is this the same as that?
Yeah.
Because no, this is not the same, because this is A or B, and then invert, you would have A or B inverted, whereas here you have A inverse and B inverse, and then out here you're going to have A inverse or B inverse, and as we have already seen, these are not equivalent.
Thank you.
So this needs to be at the output of the OR gate. You first OR, and then you invert. Yes, it is totally right to say that the NOR is opposite of OR and the NAND is opposite of the AND. Okay. So if we were looking at the NOR gate, and the NOR gate is high when all inputs are 0, right? As you can see here, when all inputs are 0, or in this case, you're going to have a high. So it is totally opposite the OR gate. And they are 0 clearly in this case, both of them. And another scenario where they are both 0 is this and that, giving us a 1 and a 1. The rest, yeah, I'm not worried that you would fail something like this. So I have an example here. Determine the Boolean expression, okay, for a 3-input NOR gate followed by an inverter. Draw the resultant circuit. So you have a 3-input NOR gate gate, I'm actually just, it's like I'm already starting with the inverter, but let me start with the expression. A 3-input NOR gate, our inputs are A or B or C, right? So A or B or C is the OR. Now, if I want to NOR, I put it, that is my NOR. They've said that it is followed by an inverter. So we invert again. And when you have double inversion that are over the same things, they cancel. It's like you have something, you invert it again. If I have 1, I invert it, it becomes a 0. If I invert it again, it goes back to 1. So you have A or B or C. But let's draw the diagram. You have a 3-input NOR gate, which is A, B, C. So obviously a NOR gate is an OR gate followed by an inverter. And they are saying that we invert again, so X. So that means at this point, I have A or B or C. I invert it, I get A or B or C. I invert that again, I'm going to get A or B or C, double. That one double again. But actually really what it means is that at this point, if I had this one and I inverted it to that, if I invert it again, it goes back to that, meaning that this double inverter goes away and I end up with A or B or C. So at this juncture then, let me give you a couple of examples that you can try out. I have simplify. Simplify this for me. I see, but I don't understand you first years. Sorry for the disruption. This is Mugerwa. If you are out of time, please go. Okay? Don't disturb my class. If you feel you are out of time, maybe you are going to perform surgery somewhere, please go. It's okay. I don't take attendance. I don't care if you attend. All right? I really don't understand when a student of first year is telling his lecturer, please leave. This is my Zoom, this is my link. I still have students that are willing to study and you are basically telling me to leave. I mean, and you are just in first year. I don't understand what is happening. But I see a number of people are telling me ABC. So clearly it is going to be A, B, C. What if I have this? A, what if I have that? The reason why this is ABC is because the inverters are over B and C, so they are 2 and so they can go. For the lower one, okay, but okay, I see all of you have A, B, C inverse. Okay, okay. So you can stop there if that is what you have. The problem with this is that this would be wrong. Actually, we cannot simplify this yet being the key word here. We are going to be able to simplify it, but at this point we have not yet studied the theorems that we need to simplify this one. But because this bar, the lower bar is over B only and the upper bar is over the whole thing, you cannot just remove. The bars that you remove must be over the same terms. Okay, so you have A, B, C over both terms, that's okay. And even if I had another bar, simplify this as A, B, and C with just one bar, because this one, these two bars, I can remove them. But because for this one, the two bars are over one B, you cannot simplify it yet. We are going to see how we can simplify that in future. Actually, not in future, in the next lecture. Let us look at the NAND gate as we get to the end of our lecture. The NAND gate is exactly opposite to the AND gate. So if you have your AND gate here, this is opposite. Oh, by the way, before we go, before we leave the NOR gate, I wanted to say that we say that the output, if we are dealing with an OR gate, is A or B. When we are dealing with a NOR gate, our output becomes A or B with an inverter. Obviously, there is an inverter, so it's an inversion of the OR operation. In the AND gate, we usually have X is A and B. If we are dealing with the NAND gate, X is equal to A and B with an inverter on top. So if I give you that one, first thing you should think about is a NAND gate. And you can see that it is an AND gate plus an inverter. All right, and you get your. Again, Joanne, to be clear, this inverter should not be on the inputs, it should always be at the output. If you move it to the individual inputs, then the output is never going to be the same. Now, from what we have seen, we have A, B, and our NAND is going to be 0, 0, 0, 1, 1, 0, 1, 1. So our NAND now will be 1, 1, 1, and 0. It will be 0 only when the two inputs are high. The two inputs are high between here, so you can see you have a 0 here. Here the two inputs are high, you have another 0. And here the two inputs are high, you have another 0. Otherwise, it will be 1. Over these places where you don't have all zeros, it is all ones, it is going to be high, and so on and so forth. All right. And actually it is here, so you can see, when it is 1, 1, we have a 0. That is very strange indeed. Okay, so I'm supposed to have, yeah. Sorry about that, I was getting confused. So yeah, so I'm supposed to have, over this is a 0, otherwise it is 1. You can see that when we have 1, 1, it is a 0. For the AND, we would be having a 1 here. And so it is exactly opposite of the AND gate. So implement the logic circuit that has this expression. Okay, Vivian? Viv?
Sorry for interruption. Yeah. Is it if we first do the AND gate, then from the AND gate we get the AND gate? I don't know if you get.
Your audio is so bad, I don't think, I can't really hear you, and I doubt anybody can hear you. So maybe you can type your question in the chat, but I may have heard a few words, but it's basically you first start with the AND gate, then you put your NOT gate. Davis, should we always draw a combination of two separate gates, or we can just use the NAND or NOR gate you presented? No. You should always use the NOR gate or the NAND gate representation. Don't draw them as separate, because we have a symbol. Of course, we know that in reality there are two gates, but we have a symbol for that combination. So please always use the symbol for the gates. If you are doing a NAND gate, you draw that gate. So let us look at this scenario. We have a circuit. They want us to implement a logic circuit that implements this equation, and they have said we only use NOR and NAND gates. So basically, we need to identify where the NOR and NAND gates are here. So we have A, B, and let us say, in fact, that let A, B be equal to yeah, you can let A, B be equal to, for example, W, and C or D be equal to Y maybe. And so we would have our X is equal to AB, which is W, and Y. We have that, and then we have that on top. But does that really help us towards where we want to go? No, it does not really help us. So C or D is what? This is a NOR gate, and AB and whatever that term is, can I say C or D is equal to Y? Yeah, and Y over that is our NAND gate. So that means that we can have our NOR gate, which is C and D. Okay, so let's say we put a dot there. I have C and D. And then I'm going to have a NAND gate that has A and B and this term, which is C or D, bar, which is the C or NOR, C NOR D. So instead of saying C or D, we say C NOR D. And we can also use the term NORD. Okay, we can say that C is NORD with D, something like that. And clear here, you're going to end up with A and B and C or D, inverted, of course, and then another inverter. And if you put 1, this is the other bit, 1, 1, 1 and 1, and 1 or 0, that one, and another inverter. You have 1 and 1 is a 1 anyway. 1 or 0 is a 1, which is inverted, and you have another inverter there. So you'd have 1 and 0 inverted. 1 and 0 inverted is 1 and 0 is actually a 0 inverted. You end up with a 1. Okay, so that I think is clear. Is it possible to have a NOT circuit using 2 input NOR gates? I think you can try and see if you can use 2 input to have a NOT circuit using a 2 input NOR gate. No, no, because a NOT circuit generally has 1. Okay, let us try and see. You never know, because with these things, whatever you think about, all you need is to try and see if it can work out. So let us say we have a NOR, and we have, let's say this is our input, and we use the same input in both. So that means that here you're going to have A or A with a bar. What is A or A, by the way? Interesting. What is A or A? A or A is A. Yes, thank you guys. A or A is A, and so you would have A inverse, which is, yes, Joan, clearly you can use the NOR gate to invert a value, to create an inverter, but because the NOR gate has multiple inputs, you just use the same value to the same input to feed into all the lines on the output side, okay? So yeah, good stuff. So basically every time you think of something, yeah, it's okay, you try it and see what it gives you. Now, I want to stop here. We have done a lot of work. We have done almost 2 hours. We've also tried with a quiz. So for those of you who have had challenges, now you know what to do next time. But I like to make them part of my course because it keeps they keep people focused on the course. So I'll continue to use them. Yeah, beyond that, have a nice week. I'll see you again on Wednesday. I might give another quiz, I might not. It's just that this time I promised you, but usually I just give them as we go along. I just think, okay, let's do a quiz. Have a nice week and see you again on Wednesday. I'm going to provide the recording to the class representatives.